Every time you see a freight train, one thing immediately stands out. At the front is a locomotive that often looks as if it rolled out of a factory half a century ago. Faded paint, boxy lines, and an old fashioned design make it seem outdated. But appearances can be deceiving. The age of a locomotive tells you almost nothing about what it is truly capable of. Many freight locomotives that are now 40 or even 50 years old continue hauling trains weighing more than 1,000 tons every single day. They operate with remarkable reliability under conditions that would have forced most other heavy machines into retirement long ago. The surprising part isn't that rail companies can't afford newer locomotives. In fact, replacing them often makes far less sense than keeping these aging giants in service.
Behind their continued operation is a carefully calculated engineering strategy. Over decades, these machines have proven themselves so dependable that in many situations they deliver better value than brand new models. But what exactly makes them so special? And why haven't modern locomotives managed to replace them completely after all these years? To answer that, we first need to understand what happens when a brand new locomotive leaves the factory for the very first time.
A new locomotive may look perfect on paper. Every component has been designed using advanced software, every system has been tested, and every calculation suggests flawless performance. But the moment it enters real-world service, everything changes. Engineers even have a name for this stage, the infant failure period. During the first months or years of operation, unexpected problems begin to appear. Components that worked perfectly in simulations suddenly fail when exposed to freezing temperatures, extreme vibrations, or the immense strain of pulling thousands of tons across hundreds of miles.
History offers countless examples. In the 1970s, both the Soviet Union and the United States introduced new generations of diesel locomotives. Each weighed roughly 138 tons, about the same as 30 fully grown elephants, and stretched nearly 20 meters in length. They were designed with enormous safety margins, yet during their early years, mechanics constantly faced unexpected breakdowns. Even the strongest machines have weaknesses that only become visible once they begin working under real operating conditions. One of the biggest dangers of introducing a brand new locomotive isn't the machine itself, it's the risk it creates for the entire railway network. During the mid-1970s, an experimental diesel locomotive suffered what seemed like a minor fuel system malfunction while operating on a critical railway line. The engine shut down in the middle of a single-track section, completely blocking traffic for 8 hours. Behind it, 20 freight trains were forced to stop. Each hour of delay cost the railway company enormous amounts of money. Factories waiting for raw materials couldn't continue production. Power plants expecting coal deliveries faced disruptions, all because of one small component that hadn't yet proven itself in real service.
This is why every new locomotive design requires years of refinement. Engineers often spend between 5 and 10 years identifying hidden weaknesses, redesigning components, and improving reliability before a model truly earns the industry's trust. For railway companies, buying the newest locomotive isn't always an upgrade. Sometimes it's a gamble.
An old locomotive has one enormous advantage over a new one. Every possible failure is already known. After 40 years of continuous service, maintenance crews understand these machines down to the smallest bolt. Repair manuals have been refined over decades, and mechanics know exactly where problems are likely to occur. If an older diesel engine develops a fault, experienced technicians can often replace the defective module within just a few hours. With a newly introduced locomotive, diagnosing the exact same issue could take several days, simply because no one has enough practical experience with its design.
Over the decades, engineers have also made thousands of small improvements. Pipes that once cracked under vibration were reinforced, gear materials were upgraded, filters were redesigned. Weak points disappeared one by one until the locomotive became an incredibly predictable machine. But reliability is only part of the story. The real secret lies much deeper, inside the locomotive's massive steel frame.
When most people look at an old locomotive, they assume it's the exact same machine that left the factory decades ago. The familiar square-shaped cab, the weathered paint, and the aging body panels all suggest that very little has changed over the years. But beneath that steel shell, the story is completely different. In the railway industry, engineers follow a simple principle. The frame of a locomotive can outlast nearly every other component attached to it. Unlike passenger cars, whose bodies are built from relatively thin sheets of metal that gradually rust and weaken, freight locomotives are constructed around an incredibly strong steel backbone. Their frames are assembled from massive steel beams measuring nearly 15 centimeters thick, roughly the width of 3 adult fists placed side by side.
These structures are designed to absorb millions of tons of stress over decades of operation. They withstand violent impacts during railcar coupling, constant vibration, and the enormous forces generated while pulling freight trains weighing more than 5,000 tons. While engines, electrical systems, compressors, and wiring eventually wear out after years of service, the frame often remains almost as strong as the day it was built. That incredible durability changes everything. Once the mechanical systems begin reaching the end of their service life, railway companies don't automatically retire the locomotive. Instead, they send it through an extensive overhaul. Inside specialized maintenance facilities, workers dismantle the locomotive piece by piece. Exterior panels are removed, the diesel engine is lifted out, wiring, generators, compressors, cooling systems, and every other internal component are taken apart until almost nothing remains. Eventually, only the enormous steel frame sits on its wheel assemblies. At this stage, the locomotive resembles an empty skeleton. Then, the rebuilding process begins. Instead of constructing an entirely new locomotive from scratch, technicians install completely new equipment onto the original frame. Fresh diesel engines, modern generators, updated electrical systems, digital monitoring equipment, and advanced control computers all replace the aging components. What emerges from the workshop is something unique, a locomotive that may legally be 40 or 50 years old, yet internally contains technology built only months earlier. Modernizing an old locomotive often delivers remarkable results. During one major rebuild project, engineers replaced an aging diesel engine with a newer model that was significantly shorter, lighter, and around 30% more fuel efficient. Despite occupying less space, the upgraded engine delivered better overall performance while reducing operating costs. The driver's cab also receives a complete transformation. Mechanical controls give way to digital systems. New onboard computers continuously monitor engine performance, fuel consumption, cylinder temperatures, and electrical output, displaying critical information instantly to the operator. Yet, despite all these upgrades, one thing never changes. Officially, the locomotive keeps its original identity. Its serial number remains the same, its production year stays unchanged. Government agencies classify it as an upgraded locomotive rather than a completely new vehicle. For railway companies, this saves enormous amounts of money by avoiding expensive certification procedures and reducing paperwork that would normally accompany an entirely new locomotive. The rebuilding process doesn't stop with the engine. The wheel assemblies underneath the locomotive also receive regular maintenance throughout their lives. As steel wheels gradually wear down after traveling thousands of miles, maintenance crews remove them and place them on precision lathes. The worn surfaces are carefully machined back into their original profile before being returned to service. Only when the steel has worn beyond safe limits are the wheels replaced entirely. This continuous cycle of repair and replacement creates something unusual. A locomotive may have a steel frame built 45 years ago, while its engine, electrical systems, sensors, wiring, and computers were manufactured just a few months earlier. To anyone watching from the outside, it appears to be an aging freight engine. In reality, it's a constantly evolving machine that has quietly renewed itself countless times over its lifetime. And that raises an important question. If these old locomotives can be modernized so successfully,
Why do many of their original mechanical systems still outperform newer designs under the toughest working conditions?
Moving a freight train isn't about speed, it's about force. A fully loaded freight train can weigh thousands of tons, and getting that massive weight moving requires enormous pulling power rather than rapid acceleration. The challenge becomes even greater because steel wheels rolling on steel rails generate very little friction. In fact, the contact area between a single wheel and the rail is only about the size of a small coin. If too much power is applied too quickly, the wheels won't move the train. They'll simply spin in place, grinding against the rails and wasting energy. That's why classic freight locomotives rely on a very different kind of engine.
Instead of small, high-speed diesel engines, these machines use enormous, low-speed power plants built specifically for continuous heavy work. Inside these engines are giant pistons, nearly 30 centimeters in diameter, about the size of a large dinner plate, with an equally impressive stroke length. Despite their massive size, these engines turn at only around 300 revolutions per minute. By comparison, the engine in an ordinary passenger car idles at more than twice that speed before it even begins moving. Lower engine speeds mean less internal friction, reduced wear on moving parts, and dramatically longer service life. Some of these diesel engines can operate continuously for weeks with only routine inspections, making them ideal for the relentless demands of freight transportation.
Modern diesel engines are designed to be smaller, lighter, and more fuel efficient than ever before. To achieve those goals, manufacturers rely on advanced turbochargers, electronically controlled fuel injectors, and highly sophisticated engine management systems. Under ideal conditions, these technologies produce excellent performance. But they also introduce new vulnerabilities. High-pressure electronic fuel injectors require exceptionally clean fuel. Even tiny amounts of water or dirt can damage delicate components, forcing expensive repairs and unexpected downtime. Older locomotive engines operate very differently. Their mechanical fuel systems are far more tolerant of contaminated fuel, poor operating conditions, and harsh environments. They may not be as efficient as modern designs, but they'll continue running long after newer engines have shut themselves down to protect sensitive electronics. For railway companies operating across remote regions, reliability often matters more than squeezing out a few extra % of fuel savings. Sometimes, the toughest engine isn't the most advanced one. It's the one that's hardest to break. One of the most surprising features of a diesel locomotive is that its engine doesn't actually drive the wheels. Unlike a truck or a car, there is no traditional gearbox connecting the diesel engine directly to the axles. Instead, the diesel engine performs a completely different job. Its only purpose is to spin a massive electrical generator. That generator converts mechanical energy into electricity, which is then delivered to powerful traction motors mounted directly on each axle. Each wheel set has its own electric motor, allowing the locomotive to distribute power smoothly across the entire train. This diesel-electric system eliminates many of the mechanical limitations found in conventional transmissions. It provides precise control, tremendous pulling force at very low speeds, and far fewer moving parts that can fail under extreme loads. It's a design that has remained successful for decades because in heavy freight service, few systems can match its combination of strength, simplicity, and reliability. The traction motors used in classic freight locomotives are engineering giants in their own right. Each motor weighs several tons and is built almost entirely from thick steel and heavy copper windings. Inside, there are no delicate circuit boards or fragile electronic components. The design is intentionally simple because simplicity is often the key to durability. The copper windings inside these motors are incredibly thick, roughly the width of an adult's finger. When the locomotive begins pulling a fully loaded freight train, currents approaching 1,000 amps surge through these conductors. The motors become extremely hot, yet they continue operating hour after hour without failure. Many modern electric motors are lighter and more compact
but they often depend on sensitive electronics and advanced control systems that can be damaged by sudden voltage spikes or harsh operating conditions. For heavy freight railways, brute strength still wins. Massive steel housings, oversized copper windings, and conservative engineering have allowed these traction motors to remain dependable for decades, proving that sometimes the most effective technology isn't the newest, it's the one built with enough strength to survive almost anything.
The incredible strength of an old locomotive would mean very little if the person operating it couldn't stay in control during long, demanding journeys. Every shift begins the same way. The engineer climbs a steep metal ladder nearly 2 meters above the ground before stepping into the cab. Decades ago, these workspaces were designed with one priority: functionality. Comfort was barely considered. Behind a thin steel wall, the massive diesel engine roared almost non-stop, producing noise levels close to 100 decibels, comparable to standing beside a jackhammer. Constant vibration traveled through the floor, while heat from the engine filled the cabin. During summer, temperatures around the controls could climb to nearly 50 degrees Celsius. In winter, moisture inside the cab often froze onto the metal walls. Working long hours under these conditions demanded incredible endurance. Today, however, these same locomotives offer a completely different experience.
During major overhauls, nearly every part of the cab is modernized. The original wooden seats are replaced with air suspension chairs that absorb vibrations from the track. Air conditioning is installed overhead, and multi-layer sound insulation dramatically reduces engine noise. Despite all the comfort upgrades, one thing has barely changed: the way these locomotives are operated. Engineers still rely on physical switches, sturdy levers, brake valves, and large analog gauges rather than oversized touchscreens or complicated digital interfaces. Every instrument is designed for quick recognition. Large pressure gauges immediately show the condition of the braking system, while oversized ammeters display how much electrical current is flowing to the traction motors. The information is clear, easy to read, and instantly recognizable, even in poor weather or at night. Years ago, railway engineers experimented with replacing physical controls with touchscreen displays. On paper, the idea seemed like progress. In reality, it quickly proved impractical. A locomotive engineer wearing thick winter gloves can easily feel the position of a switch or press a metal button without taking their eyes off the track ahead. A touchscreen demands visual attention at exactly the wrong moment. In freight rail operations, reliability and muscle memory matter far more than flashy technology. One of the greatest advantages of these older locomotives is how easily they can be repaired. Their designers expected failures to happen far from major maintenance depots, so they built the entire locomotive around accessibility. Wide service corridors run alongside the diesel engine, allowing crew members to move safely through the engine compartment even while the train is in motion. If a hose begins leaking or an oil filter becomes clogged during a journey, the assistant engineer can enter the engine room, locate the faulty component, replace it with basic tools, and return the locomotive to normal operation within minutes. No diagnostic laptop, no specialized software, no waiting for factory technicians. Everything was designed to be repaired quickly using simple mechanical knowledge. This philosophy has kept countless freight trains moving across remote regions where sophisticated repair facilities simply don't exist. Reliability alone isn't the reason these locomotives remain in service. The biggest factor is money. When railway executives decide whether to replace a locomotive, they don't focus on appearance or age. They focus on numbers. A brand new heavy freight locomotive can cost hundreds of millions of rubles, or several $1,000,000, depending on its specifications. Now imagine replacing an entire fleet of hundreds of locomotives. The cost quickly climbs into the billions. A complete modernization of an existing locomotive, however, costs only a fraction of that amount. During the rebuild, technicians retain the incredibly durable steel frame and running gear while replacing nearly everything else with modern equipment.
The result is a locomotive capable of working for another 20 to 25 years at a cost far below purchasing a completely new machine. Performance may differ by only a small percentage, yet the savings are enormous. For railway companies responsible for moving millions of tons of freight every year, that financial equation is difficult to ignore. Sometimes, rebuilding the past is simply the smartest investment for the future.
Old locomotives aren't still running because rail companies can't afford new ones. They're still running because they were built to last. With incredibly strong steel frames, decades of engineering improvements, and regular modernization, these machines continue hauling massive freight more reliably and economically than many modern alternatives. If you enjoyed this video, don't forget to like, subscribe, and turn on notifications for more fascinating engineering stories from around the world. Thanks for watching.